Welcome everybody to another edition of AP Calculus BC Live. My name is Brian Passwater. We're going to be taking a look today at one of the most important topics in all of Calc BC. When you kind of get older and look back at your life, if you talk to like your parents or somebody like that, they don't remember much about high school usually, but they remember tiny like bits and pieces. So I think a lot of people as they get older, they think back about Algebra 1 and they don't remember much about Algebra 1, but they remember the quadratic formula. They remember singing a song to memorize how to do the quadratic formula, or they don't remember much about geometry, but they remember doing proofs. And pre-calculus, they remember all the trig that they learned in pre-calculus. Well, one day when you learn, you get older and you kind of get older and move past, the classes that you're in right now. Most people, when they think back to Calc BC or Calc 2, what they remember is Taylor polynomials. That's kind of like the big encapsulating idea of Calc BC that makes it unique, it makes it important. And so there's only 5 topics that the College Board was able to include on this year's exam, and they made sure that Taylor polynomials and approximations was one of those 5 topics because it really is a pivotal, important topic that ties a lot of things together of what we've been learning, not just this whole year, but even in previous years as well. So today, we're going to start our study of it, and then Tony's actually going to continue it tomorrow because it is that important and that big of an idea. So we're going to jump right into it so we can get things done. As I mentioned in the intro, my name is Brian Passwater. I'm a Speedway high school teacher in Speedway, Indiana. And the last couple of days, I've been sharing a little bit more about myself. Now that we're getting a little more comfortable with each other. And I shared the same picture last on Monday when I was presenting. These are my 2 kids when they were younger and our dog Buddy. And I included it again today because I mentioned on Monday and Tony teased it at the end of his lesson yesterday. We're going to clone, or we're going to attempt to clone my dog Buddy. And who wouldn't want to clone him? Look how adorable he is. Such a cute dog. And so he's not a puppy anymore, but he's still pretty adorable. So we're going to clone him here in a little bit. So I wanted to continue that picture, but I'll share something different about myself. And I'm going to try to share something different each time to get a little bit to know a little bit more about me. And so today what I want to share is that I have a top 50 list. And what is it a top 50 list of, you ask, right? I know that's what you're wondering. Is it my top 50 movies? Nope, not my top 50 list of movies. It's not my top 50 list of Netflix shows that I've been binge watching during this quarantine. It's not my top 50 places I want to visit around the world. It's the same top 50 list that I'm sure everyone has. It's my top 50 list of all-time favorite mathematicians, right? And so if you have your top 50 list, you might want to get it out today and kind of brush it off, and maybe we can compare notes. But I put a big blue box on it because I don't actually want to reveal much about the list. This is a little screenshot of what was from the list. And that 719 on top is because, like any good top 50 list, I have to revise it every single summer. So in July of 2019, last summer, was the last time I updated it. I like to read a lot of biographies and learn about different mathematicians. And each year, as I learn more and kind of discover some new things, I'm able to move some people up the list or down the list, or change the list a little bit. As I like to go back and check it. So I'm not going to reveal it on here, but I am going to put it on today's Dropbox for you. That way, when you go and get the materials for today, you're able to see that list, and then you can compare it to your own list that I know that you have. And then maybe we can debate a little bit. Maybe we can talk about how we have a mutual affection for a certain mathematician. Or maybe you think I have somebody that's ranked way too high or way too low on my list, but we can discuss, who you like and who you don't like on my list. So that'll be in the Dropbox. And like we've mentioned in all of these sessions, at the bottom of each video where the comments would go is a link. And if you click on that link, it takes you to a Dropbox where it'll say Isaac Newton has shared this with you. Spoiler alert, Isaac Newton takes a prominent role on the top 50 list. I won't say whether he's number 1, number 2, or number 3, or where he's at, but he's definitely in the top 3 because of all of his amazing contributions. One of my favorite people of all time in terms of mathematicians. But if you click on that Dropbox link, you'll be able to get the handouts that we're doing today. And then each evening, our friend Ted Gott types up really detailed solutions for each of these handouts, each of these problems that he puts up there as well. So you can go back and see not just the answers, but the detailed solutions. So thanks to Ted for always doing that. And so, copy those, print those off. We always include more problems on our handouts than we could possibly do in a single lesson on here as well. So you've got lots of extra practice problems to get you ready for the AP exams. So some upcoming lessons. Well, this week we're going to finish out our study of Unit 10. This is the last unit in the Calc BC material. So today I'm going to be talking about Taylor approximations day 1. And then tomorrow Tony's going to come on and do another really amazing lesson on Taylor approximations day 2. And then Friday I'll be back to wrap up our discussion and our Unit 10 with alternating series airbound. Now, this is not a topic that's tested on the exam, but please, please, please come on Friday for a couple of reasons. Number one, it doesn't do a lot of good to create these approximations if you have no sense of how good they are, right? I mean, anybody can approximate anything. If someone said, hey, how many windows are there in New York City? I don't know, 100, a billion, 50. Anybody can approximate, but if you don't have any sense of how accurate or how close it is, the approximation doesn't really have a purpose or a meaning. And so one of the ways that we can decide how good our approximation is the alternating series airbound. So we're going to be able to tie this back to our alternating series that we learned earlier, which is tested, but also we're going to be doing more with Taylor approximation. So really, even though it says alternating series airbound, it's almost like a day 3 of Taylor approximations. And then following this week, starting next week, you're going to have 3 entire weeks chock full every day, Monday through Friday, right here at 9 a.m. Eastern, of AP Calculus, BC Prep, and Review. And each day I've pretty much told you it's going to be life-changing, amazing, the most awesome thing you've ever probably seen. And I've definitely made some FD promises in my life, like Michael Scott has said, but hands down, this might be the most generous one, is just telling you how amazing it is going to be. I hope it doesn't become an empty promise. I really think if you come to these sessions, you're going to be really, really well prepared for this year's exam. And speaking of this year's exam, I'm sure by now you've heard the exam is modified this year due to the unique circumstances that we're facing. The dates are on there for you. And I only want to highlight one thing on here because Tony and I will keep mentioning and discussing the exam now that the College Board has released a little bit more information about it. But I want to highlight the idea of this 2 FRQs, right? Typically an exam will have 45 multiple choice questions. It's about an hour and 45 minutes is how long they would give you to do those problems. And then that's followed by another hour and a half of 6 FRQs, 6 free response questions. Well, this year, because it's going to be take home and online, they reduce this to one single 45-minute test. And the first question, FRQ, is 60% of your grade. That's 25 minutes in length. And the second question is 40%, which is 15 minutes. Now, what does that mean? Well, I want to point out a couple of things to you. We don't really know exactly what the test is going to look like because it's going to be different. It has to be a little bit different, right? Because of all the unique circumstances. So we're kind of speculating. And to be, full disclosure, Tony and I know nothing more than anybody else out there, right? We have the exact same information that you do. What we have is some experience as College Board consultants and longtime AP teachers that we can kind of draw on and kind of help us predict what might appear, what might look on this exam. But again, it's all speculation. But if we're going to have a take-home test, and College Board's already announced that they realize that at your home, you're going to have access to Google. You're going to have access to your books. You're going to have access to your notes. And there was no way to really prevent students from doing that. You're going to have access to apps like PhotoMath or Wolfram Alpha, where you could take a picture of a problem and it gives you worked out solutions. So how can they write a test that can still measure your understanding under these constraints? Well, it turns out that people at College Board, the test development committee that makes the exams, ETS that makes the exams, they're all pretty wicked smart. They're the most intelligent people I've ever met in my life. And so I have no doubt they're going to come up with just a really good, fair test to really measure what you know. But it also makes me understand and think that the questions are going to look a little bit different, that hopefully we're not going to see a lot of questions where you can just type it into a calculator or look it up in a book. They're going to have to be a little bit more conceptual in nature. And so if you've noticed the problems that we're doing in these lessons, especially these AP exam practice problems that are new that we're writing each day, this is sort of how we envision the test might be looking like this year, right? It's going to be a little bit more conceptual, a little bit less just plug and chug numbers to see whether you understand it, that you can't just look something up on Google. And so take a close look at the kind of problems that we do, especially after we introduce a topic. We start going into those check for understandings and we start going into those AP practice problems. Those are really good indicators of how you might be prepared for this year's exam. And then starting next week, we're going to keep writing new questions. All the questions that we're giving you are brand new. They're the questions that I'm writing to help you get ready for this year's exam and how it might possibly look. And so try those problems each day and then see how well you're doing. And starting next week, we'll just keep generating those as we prepare for the AP exam. So at the end of each lesson, we have a AP exam practice problem that we challenge you with. And then we use that same problem as the warm up. And so this is the problem that I posed, or Tony posed, at the end of his lesson yesterday. And I've been doing pretty well with, for Tony's lessons at the end, I write the AP practice problems and we kind of work together on them. But I kind of pose these questions and Tony can tweak them or add to them or kind of give his own changes if he needs to. But I've been giving sort of the ones that he's introducing a little bit easier, and the ones that I'm giving a little bit more difficult, because then I know that Tony's stuck with the hard ones to try to explain on the air, and I can have some easier ones. Well, I got a little bit mixed up, I think, in my days. So the problem I gave wasn't totally difficult, but it was a little bit challenging, a little bit tricky in places. And so today I want to spend as much time as possible diving into Taylor polynomials and Taylor approximations. It's a really heavy topic, and I want to make sure that you can't just do examples, because remember, the examples that you see in the book are things that you could easily look up on Google or Photomath on the exam. Well, we know we're going to see a little bit more creative questions that doesn't allow you to do that on the test. So I want to make sure we understand the concept behind Taylor polynomials, and not just can we mirror or can we mimic a formula and try some problems, right? We have to get to the heart of it. And so as much time as possible on that. So because of that, for today's warm up, I included the typed up solutions that Ted got typed up for us yesterday. This is an example of how it will look. So I'm not going to go in super depth, but I would recommend and challenge you to go back and really look at these problems. But if you try them, you can compare your answers. For part A, it does ask us to find this, right? That's a little bit weird to say find something, because a lot of times my students are like, what does it even mean? Like, I found it, it's right there. It's sitting on the paper. We forget sometimes that this summation sign, the sigma symbol, is a command. Just like an integration symbol is a command telling you to do something, this is a command telling you to add something up. And sometimes with series, we actually know what it adds up to. Most of our discussion has revolved around just knowing whether it does add up to something or whether it diverges. But then we also learned that unique series that Tony taught us called geometric series, which not only can we figure out if it adds up to something, we can figure out what it adds up to. So if it says find something, especially right now in this course, we pretty much know it's going to be asking for a geometric series. And so find the sum when x is 1. So we plug in 1 and we get this geometric series, and a is 4 and r is 1/3. So we had a nice formula for that. And the answer, if you worked it out, ended up being 6. The sum of the series when x is 1 is just going to be 6. And then part B takes us back to our idea of absolute versus conditional convergence. And so now it says, well, what if x is 4? Let's kind of play around with that a little bit. Well, if x is 4, it creates this alternating series. And because it's alternating, it brings up this idea as does it converge, first of all? And if it does converge, did it converge because it was alternating, or did it converge despite the fact that, it wouldn't have mattered if it altered or not, it would have converged no matter what. In this case, it ended up being a geometric series again, where r is 2/3. So we know that it converges. And then because it's geometric, it has to be absolutely convergent. We've had this discussion of conditional versus absolute convergence, and Tony hit it on again with our ratio test yesterday at the endpoints. Well, a fun little fact, a geometric series can only absolutely converge or diverge. It cannot be conditional. The conditional part can only happen with other series that aren't geometric strictly in nature. So this was going to be absolutely convergent. And then part C, differentiating the term. So we don't get to dive into in depth the idea of power series this year, whereas power series is another big idea. It's connected really closely to Taylor polynomials and Taylor series. And we don't get to dive into that on this year's exam, but they're still important. So Tony and I have been kind of sneaking in power series in the midst of talking about ratio tests and Taylor polynomials. And these are all examples of power series. So we're working with them without really thinking much about them as power series. But one of the things we do with power series is we can differentiate them and we can integrate them just like we would a normal function a lot of times. And so if we took the derivative and we just gave you the derivative, it creates this new series called B. And then we're going to find the interval of convergence of this new series divided by n squared. And so this is really tying into the ratio test that Tony talked about yesterday. And so we apply the ratio test, we get to this conclusion of this is our limit, and that means our center was 2 and our radius was 3. So we know our open intervals between 1 and or -1 and 5. And then because we use the ratio test, we can check the endpoints. When x is -1, the series diverges, it becomes a p series, but when x is 5, it converges using the alternating series test. So this is a nice problem because it really ties in a lot of the things that we've been learning about in this unit that's going to be testable, right? The alternating series test, the ratio test, the p series here of 1 over n, the harmonic series, absolute versus conditional convergence. So it's all right here, geometric series, and one nice problem. And I hope that you did well. Keep trying those problems because they're going to give you good ideas of whether or not you're ready for this year's exam or not. So what are we going to do today? Well, we're going to introduce the idea of Taylor polynomials and approximations, which is a very important concept. And then I think even more important than that is going to be, we're going to clone the world's cutest dog. That's my dog, Buddy. You might think that your dog is the world's cutest dog, and maybe your dog is, but in my world, Buddy is the world's cutest dog. And then hopefully we're going to be able to see this connection between our application of series that we've been doing, this convergence idea, with what we're talking about today of Taylor polynomials. So in order to do these things today, I hope we can find derivatives because we're going to need to do that from way back from AB. We're going to need to be familiar with polynomials. We're going to be talking about Taylor polynomials, so hopefully we understand what a polynomial is, and then writing equations of tangent lines, which we did way back in the beginning of Calc AB as well. And we're going to see some questions like this, where we have a function like sin x, and we want to find an approximation of sine of 0.2. Now, obviously, if I wanted an approximation of sine of 0.2, you could currently just go calculator, couldn't you, and just type in sine of 0.2. Well, we're going to find ways to do that before we had access to technology like calculators. So without further ado, jump in. So before we can really talk about Taylor polynomials and Taylor approximations, let's get to this idea of cloning for a second, shall we? So here's a close-up dog, Buddy, and I went online on eBay in my free time, and I found somebody selling a cloning machine. And so this is what I bought. Here's a version of this cloning machine. It looks pretty impressive, doesn't it? And you would think maybe it wasn't that legit, when it has like random boots and balloons, but the people told me, they promised me that it was legit. It was a legit machine, right? So here's how the cloning machine works. You have to tell this machine what you want to clone, know what you're cloning. You have to tell it what you want to clone, and then it's going to do some stuff, and then it's going to kick out a result. And so we have to do is give it some characteristics, give it some traits, tell it what we're trying to clone because it doesn't know what we're cloning. So if I'm trying to clone my dog, I have to feed it some information about my dog, about how I want my dog to look, right? What are some characteristics? What are some traits? Well, when I think about my dog, I think, oh, Buddy is brown, right? That's an important trait. If I'm going to clone my dog, it needs to be brown, doesn't it? And so in the computer, we enter those traits. We tell it what we want it to match up. And so I want to tell the computer that it should be brown, and the computer is going to send that to the machine, and it's going to generate a clone. So let's go ahead and do that. Let's go ahead and tell it it's brown and see what it comes up with. So it's working, I think. Yep. Okay, it's working, it's working, it's working. So I told it it's brown, and the result, what did the machine kick out? Oh, wow. First of all, if that sound did not wake you up this morning, I don't know what will. It spit out a stick. Is that a stick? It is a stick. No, that's not a very good clone for my dog. I guess it is brown, right? If I told the machine it's brown, that's all I had to go with. It came up with, I guess, the first thing it found that was brown. There's probably a lot of things that are brown I could have come up with. That's not a very good clone. Maybe we need to tell the machine more information. Brown wasn't very specific. I don't want it to be a stick. Buddy's an animal, right? It's not a stick. So I'm going to tell my machine this time it's brown, but also don't forget it has to also match up the fact that it's an animal. So let's try that and see what the machine comes up with. If I tell it it's brown and an animal, okay, let's see what it comes up with this time. Oh, look at that. It's a teddy bear. Actually, that is pretty cute. I wouldn't be too upset about that. It looks a little bit more like my dog, at least, doesn't it? Like, at least it's somewhat resemblant if you're really far away, maybe, and the picture is kind of blurry. I don't know. But still not quite what I'm looking for, right? So I'm starting to get a hang of this machine. I should probably be more specific. So let's not just say that it's brown and that it's an animal. I should probably mention it's living, right? It's not a stuffed animal. It's a living animal. So I kick that into the machine and let's see what it comes up with. Oh, that's a Chewbacca. That actually does look a little bit more like my dog, doesn't it? But again, not quite what we're looking for, but we're getting closer, right? Each time I give it a little bit more information, it starts to look slowly more and more and more like my dog, I hope. Chewbacca's way too big. He's like 7.5 feet tall or 8 feet tall. And I already know I'm going to get a bunch of tweets and Facebook messages and emails and text telling me exactly how tall Chewbacca is. And so I don't know exactly how tall he is, but I know he's pretty tall in the movies. So I don't want him to be that tall. So let's maybe go back and tell our computer, look, it's brown, it's an animal, it's living, but small. It's not nearly as big as Chewbacca. And let's see what our machine comes up with now. Okay, I think our machine is just playing with me at this point. This is an Ewok, in case you don't remember your Star Wars history. And I don't know if it's messing with me or it's confused, but notice it created an Ewok, a little brown living animal that's small, and it also gave it a stick. So maybe it combined that first idea with the Ewok. I don't know. But let's be even more specific. How can I get better at this? Each time we're getting a little bit better. I probably should have mentioned it was a dog. Why didn't I mention that in the beginning? Well, probably because this would have been a lot faster of a presentation, not nearly as fun. But anyway, if I tell it it's a brown animal, living, small, and dog, I come up with that. Hey, at least we're in the right field now, right? Doesn't quite look like my dog, but at least it's a brown, smaller animal that's living, right? So what if I did it one step further? I kept giving more traits. And what if I meant the breed of my dog? My dog is a cockapoodle. It's a cocker spaniel and a poodle. And I include all that information. Now we get something like that. Now we're on the right track. This is actually not a picture of my dog. It is a brown animal living small cockapoodle, which is nice. But it looks a lot more like my dog than the other things did, at least. Just so you know, this is a modern, up-to-date picture of my dog, Buddy, here, looking like he's tired of my questions. Stares at me like that when I told dad jokes a lot of times. He knows. But you know, it's a little bit better, isn't it? This dog on the bottom is probably a little bit better bred in terms of they probably give it a bath every day. Buddy probably could use a bath, but he's not getting one every day. But it's a better idea. So this is the idea behind Taylor polynomials. So we can take a similar approach to clone functions. So it was obvious why we would want to clone Buddy. He's adorable. Who wouldn't want to have two of those dogs running around, right? Of course you would want to clone him. Well, why would we ever want to clone a function? Who looks at a function and says, man, I wish I had two of those. You know, I'm going to print one off and put it on my wall in my room, hang it up on a poster or something and carry one in my pocket, right? That's kind of weird, isn't it? You know, I'm going to take that function, I'm going to tattoo it on my arm. Who would ever do? Oh yeah, some of us would. Actually, it would be kind of cool to take a tattoo of the function on your arm. But anything else is kind of different, right? But why would we want a function? Well, we're going to talk about why. But it's this idea of a Taylor polynomial is how we're going to clone functions. So what is a Taylor polynomial, right? It's a pretty important word, but what exactly is it? Well, let's consider the function e to the x. F of x equals e to the x, and I included a nice little graph of e to the x right here on the screen. Well, imagine it's the year 1715. Why the year 1715? Because that's the year that Brooke Taylor, pictured here in this in the slide here, that's the year that Taylor published a lot of his results and information about his studies of these polynomials. Now, he wasn't the first one to come up with these ideas, but he was kind of the one that had the most exhaustive research and took it kind of the furthest, in terms of mathematics. So he's kind of got his name tied to it now. He gets kind of credit for it. But 1715 was when he published a lot of his information. So back then, we didn't have cell phones, right? We didn't have iPods back then, believe it or not. We didn't have computers or technology. Even books weren't as common in normal households. And so how would you find e to the 0.1? How would you do that? Right now, we just type it in our calculator and get some decimal and just say, okay, perfect, right? But how would you have any concept of how big that was without a calculator? Well, we don't really have, even now, a simple way to do that. There is no easy way to do that. But what we can do is try to find a way to approximate those values. And that's the idea behind Taylor polynomials. What they're going to do is they're going to take ugly functions. I'm going to call e to the x an ugly function, not because it looks ugly. I'm going to call it ugly in the fact that it's a little bit more complex, that we can't just plug numbers in like decimals or other random numbers and compute it by hand very easily. And we're going to replace them with prettier ones. Well, if e to the x is an ugly function, what is a prettier function? What's a nicer function to work with? Well, it turns out that polynomials are really, really nice. Because polynomials, right? If I think about a polynomial, I'm just going to make up an example here, like 5x squared minus 1/2 x plus 7, right? That's an example of a polynomial. On a polynomial, you can plug in any number that you want. I could plug 0.1 into this and work it out, because polynomials only require basic arithmetic, meaning you can add, you can subtract, you can multiply, and you can divide. If you can do those four things, you could plug numbers in and then compute it. It might take some work, right, doing it by hand, but at least you have a way to do it. And so if we could somehow clone or create a new function that looks kind of like this e to the x function, but it's a polynomial, that will allow us to approximate these more ugly functions. So here's some examples of ugly functions that you might see on the left-hand side, things that we might be looking at this semester, like e to the x, natural log, sine, cosine, invergent. Those are all ugly functions, because if I said plug in 0.1 to any of those, you really would have no idea of how to do that without a calculator. Well, on the right-hand column are examples of some nicer, prettier functions. You might not think they look that nice. They look a little bit more complicated, but they're nicer in the sense of, if I was trying to plug 0.1 in, for example, I could do that into any of these and work it out by hand and get an answer, right? Now, I think beyond the pretty and the nicer functions, we also have the prettiest of functions, the prettiest of things, and that's going to be this nice picture of my two cats. They're feeling a little bit jealous and left out because Buddy was getting all this attention. So yesterday, they were laying on my couch and they were snuggling up and saying, "Hey, take a picture of us." They're pretty photogenic. So this brother and sister showing some brotherly love, right? So how are we going to create a polynomial that approximate a function? Well, essentially, just like we did with Buddy, we're going to clone the function. With Buddy, we found properties of Buddy, right? He was brown. He was an animal. We took different characteristics and we made sure that whatever we created had the same exact characteristics. So we're going to do the same thing with functions. But what does it mean to say we're going to clone the traits or the characteristics of a function like e to the x? Well, what we're going to do when we say that is we're going to clone a value, right? A point on a graph would be a trait. And then the other things that are characteristics are the behaviors of the graph. What's the slope of the graph? What's the second derivative, the concavity of the graph? What's the third derivative and the fourth derivative? And the more traits and the more characteristics that we match up, the more that our clone will start to look like the real deal. And so how do we do that? Well, the first step is we're going to pick a random point, C, that's going to be an X value, by the way, where F, and F is the function that we're trying to clone, and P of X, and P of X is going to be the polynomial that we're creating. And so I want to take a quick side note and show you some notation for a second. When we create a polynomial, we're going to call it P sub n, typically, where n is the degree of the polynomial, right? We could create a first degree, a second degree, a third degree. Remember, the degree is the highest exponent of the polynomial. And we're going to write our polynomial like this: a sub 0 plus a sub 1x plus a sub 2 x squared. And we're going to keep going up and up and up until we get to that highest power, that n exponent, the degree of the polynomial. And so we use these letters, a sub 0, a sub 1, a sub 2. Typically, when you learn things like quadratics in algebra, we call it like ax squared plus bx plus c. We use letters like a, b, and c. We don't want to use that lettering system because there are some polynomials, we won't see them in the course right now, but you might have 30 terms, right? It goes all the way to x to the 30th. Well, you're going to run out of letters pretty soon. So it's a little bit easier and simpler just to call them a sub 0, a sub 1, a sub 2. And you can see how that's already connecting to our idea of a series that we were learning with convergence this last week and a half, right? So this is going to be our polynomial kind of equation. And so we need to make sure that whatever we create in our function we're approximating, that they have a point in common. That one trait is they have the same point at that value of c. And c is going to be our center. We're going to call it centered at c. And so this example that I have here in the picture, the center is going to be 0. This is the point, right? When x is 0, that's the point where all the action is going to happen. As we start making our clones and matching up properties and characteristics, it's going to be matching at the center right there. So we have to come up with an equation or a polynomial that goes through that same exact point, right? Well, here's the issue with that. There's infinitely many polynomials that would go through that point, right? If I said, hey, a graph or a polynomial that crosses that same point as the graph, well, our machine could generate all kinds of things, couldn't it? I mean, there's a whole bunch of polynomials it can make, and they may not be very good. You might kind of get a stick right back. The result could be a stick. We're like, okay, I guess it does go through that point, but it really looks nothing at all like what I'm trying to actually clone, right? And so we want to be able to give it more information. We want to be more accurate, so we don't return things like a stick, for example, for our clone polynomial. So what do? Well, we can match more traits. So one other thing that we can match would be their derivatives, right? What if I said, don't just have a point in common, but at that center, whatever we create should have the same slope as our function, right? We want to have the same slope right there as well. And then if we do that more and more and more, the more traits that we create that match up, the more that our polynomial is going to look like the true graph, okay? So let's look at a couple of examples so we can take some of this abstractness and put it into some concrete ideas. So we're going to create a first degree polynomial centered at x equals 0 for the function e to the x, and e to the x is the same graph that was given there. So typically when we're writing one of these polynomials, there's 3 really important pieces of information in the problem that we need to know. The first one is the degree. This one is a first degree, meaning the n value is going to be 1. Remember, first degree means the highest power of x is going to be 1. If it was a second degree polynomial, we'd go all the way up to the x squared term, and third degree be x to the third, on and on and on. So we need to know what degree it is, how many things we're matching up. Second of all, we have to know what the center is. In this case, the center is 0. And hopefully it makes sense why we would pick 0, because when you pick 0, remember, we're trying to match up a point on the original graph and derivatives on the original graph with whatever we're trying to clone, right? And so whatever point you pick, that center, you really should know the value of the original graph, meaning I can't match up the original graph with my polynomial that we're going to create unless I know the actual point and the slope on the original graph. So it wouldn't make sense to make the center like 0.1, for example, for e, because I don't know what e to the 0.1 is. I don't even know what the point is on the graph. If I don't know what that point is, I can't match it up, right? So we have to pick a point that we know, and the problem will tell you what center to use. And then we have to also know what function we're trying to clone. That's f of x. F of x is what we're trying to match up. So we have all this information, and what helps me is to be organized. And so if I'm trying to make a first degree polynomial at 0, then I know it's going to look something like this. P sub 1 of x, the 1 is, remember, the degree. And going back to our little formula that I wrote up here, P sub 1 of x is going to be a sub 0 plus a sub 1 x, right? This is my first degree. I would stop there because the x has a power of 1. And so if I'm trying to create a polynomial that looks like this, well, to do that, Your job is figure out what numbers go there. What's a sub 0? What number would go there, and what number would go where a sub 1 is? And you can't just pick random numbers. We have to find the specific numbers so that the points on f and our polynomial are the same, but also their derivatives are the same. Well, here's how we can do that. I'm going to kind of make some more space down here. The first rule is the f of c, the point on the graph of f. Remember, f of c is f of 0 because c was 0 at our center. I need the graph at 0 of f to be the same answer of the graph of p at the center, right? We're matching things up. This is how we're matching up the characteristics or the traits at the center. Well, we know what f of x is. F of x is e to the x. And so f of 0 is just going to be e to the 0, because that's what f of x is, which happens to be 1, right? F of 0 is 1. Well, p sub 1 of 0, if I plug 0 into my polynomial here, I'm going to get a sub 0 plus a sub 1 times 0. I'm plugging 0 in for x. So they're telling us if you plug in 0 to both equations, you should get the same answer. Well, if I plug in 0 to p sub 1, I get just a sub 0, which means this answer and this answer are supposed to match up, right? That was one of our first requirements, that we have to clone and make sure they match up. And so that tells me that a sub 0 then is 1. Perfect. We already figured out one of our answers. But I also need to figure out a sub 1, don't I? And to figure out a sub 1, we're going to use the fact that we need their derivatives to match up. Well, what is the derivative of f? Well, if f of x is e to the x, the derivative is still e to the x. This is the reason why we choose e to the x for our first example in most textbooks and most Calc BC courses, because the derivatives are really easy to work with. And so f prime of 0 is going to be e to the 0. I plug 0 in, which is still 1 in this case. And then I need to find p prime of x as well. Remember, we're trying to match up their derivatives. And so I took f's derivative and plugged in 0. Let's take p's derivative. Well, if p is a sub 0 plus a sub 1 x, the derivative a sub 0 is a number. That's just going to go away. And a sub 1 times x, that derivative just becomes a sub 1. It's just the constant in front, right? And so p prime of 0 is just a sub 1. We plug 0 in for x. There is no x, so we just get whatever constant is there. And those two answers have to match up, right? We're cloning these ideas, we're pairing them up, which also means that a sub 1 is also 0. So we now have found enough information to write our polynomial. Our first degree polynomial that would mirror or clone e to the x is going to be 1 plus 1x. This is our first degree Taylor polynomial centered at 0 for e to the x power. And here's a little picture of what it looks like. In blue, this is our original function e to the x. And then in red, that's what we just created. That's our polynomial 1 plus x. And notice at the center of 0, they match, right? They touch right there. They have the same point. And also at the center, they have the same slope. So how good of an approximation is this? Well, we know that we make approximations when you're close to that center, right? When you're near the center, the two graphs are pretty close, right? They look a lot like each other. Now, the further out we go away from that center, generally speaking, our approximation starts to look less and less and less like the true graph, right? So this is kind of like that teddy bear. I matched the brown and I also matched it's an animal. So that teddy bear looked a little bit more like Buddy, but still not a perfect idea. And so how are we going to get better and better ideas or approximations? Well, we create more and more matches. And so the same type of problem, we could create a second degree polynomial. Well, a second degree polynomial would be a p sub 2, and that would be a sub 0 plus a sub 1x plus a sub 2 x squared. And if we're going to create a third degree polynomial, the good news is we've already cloned the first two things, right? We already know from our last example that a sub 0 is 1 and a sub 1 is also 1. So we know those two things. So our second degree polynomial is going to look like 1 plus 1x plus something x squared. And maybe you're thinking, Oh, it's always going to be 1. It's always going to be 1 in front. This is pretty easy. Well, if only it was that simple where the answers are always 1 for the coefficients, this would be a lot shorter of a lesson, but it's not going to work out that way. So in order to make sure that we create a match for a second degree polynomial, we've already matched the fact that they have the same point, and we've matched that they have the same derivative at the center. Now, to continue this, we have to make sure that the second derivative at the center of our function matches. We're going to clone that with the second derivative of our polynomial. So we need to take our polynomial here and come up with the second derivative. This is a p, by the way, in case you can't see that very well. So here, p prime of x, the derivative, is just going to be 1 plus 2a sub 2 x, right? And the second derivative for our polynomial that we're trying to create is just going to be 2 times a sub 2. And we know that to make our clone, we have to make sure that their second derivatives of what we're trying to clone and what we're creating pair up. And so f double prime, well, luckily, since we're working with e to the x, f double prime is just e to the x, right? It never changes. So f double prime of 0 is just going to be e to the 0, which is still 1. And that needs to match up with p double prime of 0. Well, if I plug in 0 for my p double prime, we're plugging 0 in for x. Well, there is no x, so we just get 2a sub 2. And these two things have to match, right? We're cloning these things, we're pairing them up, and we're making sure that they have the same properties, which means that 1 has to be 2 times a sub 2, and then dividing by 2 tells me that a sub 2 is going to be 1/2. So now we found our a sub 2, which means our second degree polynomial that we just created would be 1 plus 1x plus 1/2 x squared, like that. And here's an example. Here's a picture that shows the 3 things that we've just done. I'm going to kind of slide it up a little bit so you can see it here. In blue, that's our original e to the x problem. And then in red, this is what we did on the first example, created a first degree linear polynomial. By the way, you recognize those first degree ones all last semester when you were learning about tangent lines and creating tangent lines. That's what you were doing, right? You were really creating a first polynomial approximation. That's what a tangent line is. But now we're extending it. And look how much nicer in green our second degree polynomial looks. Now, again, it still touches that same point. They have that same thing in common. They have the same slope, right? We have 2 things that match up. But on top of that, at the center, I made sure that our polynomial in green had the same second derivative, the same concavity. So now it starts to look more like our function. It's a little bit better. Close to the center, it's almost indistinguishable from the true polynomial. And as we get further away from the center, it stays closer for a longer period of time, right? And if we kept going, as you can imagine this, we could keep matching up characteristics. And the more things you match up, the more derivatives you match up, the higher degree polynomials that you can create, and the better it looks. And if we did this infinitely long, right, there's infinitely many derivatives that we could pair up, it would just be infinitely long polynomial, which is called a power series or a Taylor series. And so this is how all these things are going to tie together, that if we kept going, we could create a perfect model that would create a representation for something like e to the x or sine of x or something like that. So I want to jump ahead a little bit, and I know that's almost 9:45, and I want to share something with you because we just saw one quick example, right? And that was with e to the x. It shows you how this works. But do we have to go through the whole process over and over again every single time? Or is there kind of a general rule that we can follow? And so what you'll see in every textbook is this sort of box that will say, this is the definition of a Taylor polynomial, right? Centered at C. Well, the example that we did was centered at 0, but it won't always be centered at 0. So it's centered at C. So x equals C is our center. Well, let's see if we can quickly develop this idea behind a general formula, right? And so we're going to use that same process that a polynomial, right? We're trying to create a clone that looks like this. We're trying to create some nth degree polynomial centered at C. So it looks kind of like what we saw before, but instead of every x, it becomes x minus C, because we're centered at that value of c. So it's a sub 0 plus a sub 1 x minus c, a sub 2 x minus c squared, on and on and on. Well, if we're going to create a clone like this, here's what we have to do, right? I want to make sure we don't get lost in all this proof that we're about to look at. We have to come up with values for a sub n, right? In order to create our polynomial, we had to know what those numbers were in front. And every problem is going to have different numbers depending on the equation, the center, and what kind of degree you're creating, right? And so how do we figure out what a sub 0, a sub 1, a sub 2 is? Well, to find it, we remember to create our polynomial, we're matching things up. That our polynomial, whatever the function is we're creating, it may not be e to the x, it could be anything. We need our function and our polynomial to be the same at the center, right? The same point. We also need their derivatives to match up, right? We're giving more and more descriptors. We want their second derivatives to match up, and their third derivatives, and their fourth derivatives, and their, on and on and on, all the way up to the nth derivative. And if we keep matching up those things, we keep cloning those properties, then our polynomial will look more and more like the true function that we're trying to kind of replicate, right? And so we do that by creating these ideas, and by doing these, by setting these things equal. That's how we're going to find all of those a values. And so we're going to do that by finding the derivatives, right? We know what p is. So what would p's derivative is? If I'm going to match up, right, f prime to p prime, I have to know p's derivative. Well, p prime of our polynomial, p prime of x, well, here's our p of x. If we took this thing's derivative, a sub 0 is going to go away. It's just a constant, right? It's gone. A sub 1 times x minus c just becomes a sub 1. It's just the constant in front because we have a degree of 1 here. And then our second term, this derivative, we bring the exponent down in front. It becomes 2a sub 2 times x minus c to the first power. And then the next term, we bring the 3 down in front. It becomes 3 times a sub 3 x minus c squared, right? We subtract 1 from the power. And if we use the chain rule, we're multiplying by 1 because the inside x minus c's derivative is going to be 1 each time. And we could keep going, right, all the way until we got to the last term, and it would be n times a sub n x minus c to the n minus 1 power, right? That's our first derivative. Now, we would keep doing that. We to keep taking derivatives because I need to pair up every single one of those. Well, we're not going to have time to do all that right now. So here's sort of what it's going to look like, and I hope that you can trust me. If I took this term's derivative, find the second derivative, the a sub 1 is going to go away, and then this next term is just going to be 2a sub 2, and then it's going to be the 2 comes in front for the next term. It becomes 3 times 2, a sub 3, x minus c, and it kind of keeps going and going and going. And we could keep doing that all the way until the nth derivative. And when we get to the nth derivative, all we're going to have left at the end is just n times n minus 1 times n minus 2 times n minus 3, all the way down to just 1 and then times a sub n. There won't be any variables left. We took all of the derivatives until we got to a constant, right? And remember, the ultimate goal here is how do we find all of those a values? How do you find a sub 0, a sub 1, a sub 2? Well, the way we find those is by setting these things equal to each other. I need f of c to be p of c, right? That the function we're trying to replicate is going to be the same as the polynomial at the center. So we need f of c to be p of c. Well, we know what p of x is, right? That was our original polynomial. If I plug c into all of these terms for x, right? If I plug in c, plug in c, plug in c at the center, all of these terms are going to cancel because c minus c is 0. They're all going to go away, and all we're going to have left of p of x is that first term, a sub 0. So it turns out we need to figure out what a sub 0 is. Well, it's always going to be just f of c. Now, we don't know what f is, right? We don't know what the function that we're trying to copy is, but whatever the function is, if I plug in c into that function, that answer will always be a sub 0. And then we can continue this process by matching up their derivatives. If I want f prime to equal p prime of c, well, all I have to do is plug in c into that derivative. If I plug in c into the derivative, all those extra terms go away, right? If I plug in c there, they all go away, and all I have left is that first term a sub 1, which means that a sub 1 is f prime of c. And now we have a way to find a sub 1. It's just the derivative of f at c. And if we continue this process, it's going to be a little bit more complicated because for the second derivative, if I plug in c for all those values of x, we're left with 2 times a sub 2. Remember, I need to know what a sub 2 is. So by dividing both sides by 2, a sub 2, which is that next coefficient, is going to be f double prime of c divided by 2. And if we continue this process, what we're going to learn is all of those a sub n values are going to be found by just taking the nth derivative of our original function and dividing it by n factorial. And so this leads us to this general form, which is this. The definition of an nth Taylor polynomial and an nth Maclaurin polynomial is going to be this equation right here, where p sub n, this is our polynomial we're trying to use to approximate f, is going to be f of c. Remember how our a sub 0 is just f of c? Then our a sub 1 was f prime of c, and then our a sub 2 was f double prime of c over 2 factorial. And so if we keep going, this is sort of our general form. And so how do you create a Taylor polynomial? Well, all you have to do, your job, is you have to find all of these f values. Whatever function you're trying to clone, you have to find the value at the center, the derivative at the center, the next derivative at the center, and you keep going and you find values and you plug those values into this equation, and that is our Taylor polynomial. Now, we also have something called the Maclaurin polynomial, which is a special case where what happens when the center is 0, like we saw on our e to the x example, right? On our e to the x example, the center was at 0. And so it makes the problem a little bit simpler. If c is 0, f of c is just f of 0, right? I'm plugging in 0 for c, then f prime of 0, and then x minus 0. So it's just going to be x. And then if you keep plugging 0 for all those c's, it's just kind of a simpler version of the Taylor polynomial. We call that a Maclaurin polynomial, right? As Pam Blees said in the office, there's a lot of beauty in ordinary things. Isn't that kind of the point? When you look at this equation right here, it's really a beautiful thing when you get to know it. At first, right now, if this is your first time seeing this, you're probably thinking, what is happening right now? But when you see it, you realize, and we're going to reinforce this tomorrow and again on Friday, how beautiful it is and how powerful this is, right? And so I want to just create or try one quick example together that we can do here before we wrap up. And I'm going to do this on practice 3 from the Check for Understanding. And I want to pick this one because it shows where we don't actually even know the function that we're approximating. On our first examples, I told you it was e to the x. It's possible we don't even know what the function is we're trying to mirror or clone, but as long as we know properties about it, we can do it, right? And so for practice 3, it says a function h. So we don't know what h is. There's some random function h. We don't know what the equation is, but we're going to find a third degree Maclaurin polynomial for h. Remember, the importance here are, number 1, it's a third degree, right? That means we're going to go all the way up to the x cubed term. Number 2, it's Maclaurin, which means the center at 0, c is 0, and then the function is h. Well, going back to our Taylor polynomial, our formula, the formula for a Taylor polynomial going to be, in this case, actually, I don't have to say p sub n. We know we're doing a third degree. It's going to be p sub 3, right? Our polynomial is going to be f, or in this case, h, right? We're using our function of h. H of 0, we're using the center, plus h prime of 0 times x, plus h double prime of 0, x squared over 2 factorial, plus h triple prime at 0, x cubed over 3 factorial. This is the formula that we showed in that box, right? So I like to write out the general formula down first, and then all I have to come up with my answer is you have to find all of these values right here. That's what your job is. So h of 0, well, guess what? The problem told you h of 0, it's 2. That's pretty cool. H prime of 0, I told you that too. It was -1. Hey, this isn't so bad after all, is it? Now, the other two, I kind of stopped giving you information, didn't I? Well, but I did tell you this nice little formula here that says the nth derivative at 0 is just n squared over 2 factorial. So if I want to find the second derivative at 0, it's going to be 2 squared over 2 factorial, right? I'm plugging in 2 for n for the second derivative, which is going to give me 4 over 2, which is 2. So h double prime of 0 is 2. That wasn't so bad. And then finally, the third derivative of h at 0, according to our formula, is going to be 3 squared. Now we're plugging in 3 for n over 3 factorial. Well, 3 squared is 9. 3 factorial is 6, which is going to be 3 halves. And now guess what? We have all of the information that we need to create our polynomial, our third degree polynomial for this function h. Now remember, in this case, we don't even know what h is. We don't have a picture of it, an equation of it, but we knew enough information about it at the center to create an approximation. And so our approximation is going to be 2, that's what h of 0 was, minus 1x, right? I plugged in -1 or h prime, and then h double prime is 2. So that's going to be 2x squared over 2 factorial for my third term. And then finally, the third derivative is going to be 3 halves x cubed over 3 factorial. It looks a little bit complex and ugly, but guess what? That is a third degree polynomial that would approximate h based on the information that was given. Wow, that was a lot of information, right? So I want to hopefully let you try this and try some of these before we start finishing up tomorrow. And don't worry, Tony tomorrow is going to come back and really do a lot more examples with us. I did a lot of the front loading of the instruction, and now Tony can do a lot more concrete examples, especially some things that you might see on the AP exam. That last example that we did, the check for understanding, would be a good example of what could be on the exam this year. So today, we looked at power series and how they could be used to associate functions on an interval, and we did that through the lens of Taylor polynomials. So your AP practice problem is this question right here. It's a fun little problem. It's a little bit challenging, but you have everything that you need to know, and it ties in some older things with some newer things. So give it a go, and then check your answers late tonight, and then make sure tomorrow morning you tune into Tony as he kind of walks us through these answers, right? And as Michael Scott would say, would I rather be feared or loved? Easy. Both. I want people to be afraid of how much they love me. You might be fearful of Taylor polynomials when you first see them, but I think eventually you're going to come to love them, especially as I put it together tomorrow and Friday to give you a more complete picture of how these things work. But they really are a beautiful, beautiful thing. So as all remember, the College Board has tech issues that they can help you sort through. So email or reach out to cb.org/tech if you're somebody you know has any problems with technology. And then quickly, briefly here real quick, as we're wrapping up, we've been doing these AP tweet apps and stuff. I have a couple of shout outs here for shout out to Mr. Rabchuk for the most epic calculus class the world has ever seen. Chocolate chip cookies for you once I aced this BC exam. And then from a teacher, so proud of my AP BC students persevering through our series unit. That's what we're on right now. Fighting the good fight, absolutely. So thank you guys so much. As Kelly Kapoor would say, I mentioned this again on Monday, you guys, I'm like really smart now. You don't even know, right? You guys are doing Taylor polynomials. That is incredible. So kudos to you. Great job. Try these problems in the Dropbox. The solutions will be on there tonight. And then tune in tomorrow for Tony's epic lesson that will wrap this up and give you a better understanding, lots and lots and lots of more examples to get you ready for the AP exam. So thank you guys for watching. Tune in tomorrow for Tony, and we'll see you then. Thanks.